Well, welcome, folks. We'll wait for some more people to maybe show up. Let me turn off Copilot so we can't cheat. And write a little introduction. So Zymposium on basically implementing Hindley-Milner. Damas, Hindley-Milner, Langton. Because my variation, my contribution will be to probably break it slightly and make it worse. All right. But yeah, unfortunately, Adam is not here today because he is teaching, what was the other word? Presenting at Scala IO in France, in Paris. I think he just gave the keynote. It's probably wrapping up. But, you know, he's got to meet and greet and do all sorts of other conference activities. So he will not be here today. But we'll just give it a few more moments. Nonetheless, since Adam is out of the building, I thought I'd do something entirely impractical. While the teacher is out of the room, do the equivalent of, shooting spitballs at each other, which would be figuring out how type inference works, sort of, at least one variation of it, which is Hindley-Milner. So we're going to talk about today's topic. I guess I already wrote that above, but whatever. Today's topic is writing a type inference algorithm from scratch, which is hopefully going to be Hindley-Milner. Worst case, I'll mutate it accidentally, and it will be Hindley-Milner, Langton, and slightly broken. But yeah, let's give it just another minute, and then I'll dive in. Let me also check the chat. So I've got to, hello, it's asking for a passcode. Oh no, shouldn't have a passcode. Let me send the link to that room. Yes, unfortunately. Hopefully that helps. And I'll do a little ping. But yeah, we're almost at quorum. But meanwhile, if you have any questions, feel free to ask them. Maybe it might be, generally I say, use Discord, but that's because there are two of us usually. But with the Zoom chat, I will see a little red dot in the Zoom chat. So maybe prefer Zoom chat if you really want me to answer something pronto. Zoom chat's disabled. Everyone, there we go. I think I've just enabled it. Yeah, usually, hello, yes, welcome. Hooray, you're free. Don't go evil Hulk on us. I'll also paste the Discord link in case, usually we chat in Discord. But Discord doesn't give me nice notifications, and Zoom will have this since I have to have the horrible Zoom bar superimposed atop every screen, I may as well get the most out of it and have people chat there. But obviously you can see where I'm looking right now, which is at Discord in case something interesting happens. Mutated to support subtyping, yeah. Yes, we're totally going to continue. So last week at the hackathon, Adam and I walked through basically writing Zio from scratch, but using all of the learnings that went into the runtime in the last year. So we went a bit faster than we did in our previous sessions, but also hopefully things get simpler from here on out. We sort of pay the cost upfront. And there's this new sort of actor system that kind of is what the new fiber is. It's this mini actor. Yes, and I'll ask Adam to push up the code. I think I saw somewhere that he would push it up. Yes, here. Oh, but that was a few days ago. So he's been traveling. So, but I'll ping him. Exactly. Actors all the way down. But yes, today we're not going to be implementing actors. At least I don't think so. If I do everything right, I don't think this type inference algorithm will use actors. And we don't really worry about performance just yet. We just want to make sure we get it right and understand the concepts. So today, without further ado, let us get into it. So yeah, I'll try to check back in the Discord chat every once in a while. But once again, if there's something really pressing, if you use the Zoom chat, I think I should see like a red dot appear on my screen. So last chance. Let's begin. And there's a good chance maybe someone knows more about Hindley-Milner than I do. I'm definitely sort of learning on the job here. I've looked into it over the last few days. I've looked into it in the past and mostly hit my head against it. But by deciding to do it, deciding to teach something is a great way to force you to learn it. So if you ever want to learn something, commit to a conference talk or have a weekly Scala session where you have to teach people over the internet. It lights a bit of a modest flame under your butt. And I'm proud to say I am closer to feeling like I understand it more than ever. Part of the difficulties with understanding a whole bunch of these sort of more advanced functional programming topics is that the only resources can be a bit sort of abstruse and technical, basically white papers that are written for academics, by academics. For academics, by academics, which is not great for me because I'm not either one of those things. I'm just a dummy. I'm just a dummy on the internet. And so it's a bit difficult to parse all the syntax, to sort of tease apart what's relevant, what's not relevant, what's only important for sort of mathematical accuracy versus what do I need to implement the damn thing. Usually there aren't many implementations. Luckily, I was able to find sort of an implementation. I mean, no, it is an implementation. It's just written in Haskell. And I think I linked one of the resources here is Write You a Haskell by Stephen Deal, which is an unfinished book, unfortunately, but it had a really sort of huge ambition, which was to show you how to write. I mean, you could see the unimplemented chapters, basically how to write Haskell starting from the very beginning, getting into really complicated stuff, and then basically the core of Haskell, and then doing code generation down to C and LLVM, and maybe even adding new features to the language. So hugely ambitious, unfortunately, never was finished. But those chapters that, the unimplemented chapter 12 is how to print to the terminal. No, I think we'll be able to get printing to the terminal today, actually. At least that's how we're going to debug it. So a little bit. So really cool. Unfortunately, some of these they sort of are different levels of completion. I remember reading this years ago, trying to understand what was going on, and I pretty much just gave up. But today, or the last few days, under anticipation of needing to teach it, under the time pressures, I basically looked at a couple of different implementations and rewrote them in Scala, and then simplified them, and then built them back up, and then tried to figure out like what the heck is important, what's not important, what does it all mean? I think that's I like to really try to. I'm very anxious until I fully understand something. So I get very nervous if I'm just sort of cargo culting, or if I realize that I'm cargo culting. One of the benefits about teaching is that it makes it very apparent to you where sort of the unstable nodes of your knowledge graph are. Because you're going to have to teach something, and I notice when I just sort of repeat some phrase, some shibboleth, instead of actually breaking that shibboleth down into its more nuanced components, and it makes me uncomfortable. And I like to understand things. So I think I've done a little bit of that. I'm not going to say I'm a master of Hindley-Milner type inference, but I think I can at least if you don't know anything about it, get us somewhere, and I think I can actually implement a version that will work for our intents and purposes now. Hopefully, we'll see what happens. Okay, that's enough preamble. Let's get to looking at code, because I, with my simple mind, like to look at Scala code. I understand Scala code. Ideally, relatively simple Scala code with minimal abstractions, just to really understand the core principles here. So we're not going to write the most type-safe code necessarily. We're not going to use, we're just going to throw exceptions. We're not going to handle some edge cases. We're going to, fail fast, but hopefully this will be a nice pedagogical model of understanding a bit of Hindley-Milner, at least one implementation of it. I know if you go to the Wikipedia page, there are like 20 different notes of all these different algorithms. Algorithm J, algorithm, where is algorithm? Algorithm J. I know there's like an algorithm F or system F. Maybe that's something else. I don't know. There's so many different variations. I don't know which letter this has. Maybe algorithm K, we'll call it. I don't know what it is. It's just whatever. It's sort of some smorgasbord from what I understood, but it seems to work. So, and furthermore, I think I understand why it works to some degree. So let's start from the basics and let's kind of write some stuff, try to get something working, and until we sort of force ourselves to complicate the system by running into a wall or two. I like working like that. Cool. Okay. So now for real, what do we have? Well, first we're starting with this abstract syntax tree of a very simple, very, very simple language that only has a few terms. So first of all, some terminology. The terminology term. This is basically something that you can construct in the language. So generally there are these two words. There's the world of terms, two worlds. There's the world of terms, and then above it, there's the world of types. And terms will have types, but they're different. Terms are essentially what exist at runtime, and types are these annotations that we're using that, to make sure our program makes sense. And it's these contracts that we superimpose upon our programs. The purpose of today is to take a term and infer. So we're going to have this method essentially called infer, which is a function from terms to types. Now, technically, it can fail for a variety of reasons. Not every term you can construct is so-called well-typed. So our goal is to get the types out of well-typed terms, otherwise blow up. We're not going to worry about giving a nice error message for now. We're just going to blow up. So here's our language. It's a little difficult to maybe see how these all fit together. Basically, it's a sealed trait hierarchy. So a term is either a variable or something called an application, something called a lambda, an if then else, and then only two literal values. So the actual literal values we have are either a number or a Boolean. And we can't even add the numbers together. We just have numbers. The Booleans we can at least use in our if then else as a condition. But let's sort of just start by making some terms in this language to get an idea of what's possible. So I think I have another, where'd it go? Infer. I have this other file here. Can we call it application? Can we not call it application in Lambda? Yeah, we can totally change anything, but let's talk about what they are first. And I'm totally happy to different names. Kind of just went with that because that's what the different examples I've seen used. But basically, here are a couple of examples of our language. So one is, this is going to be our syntax for creating a lambda, which is basically an anonymous function value. And what this would do, x to x, that's our term here. This is just basically the identity function. So in Scala, identity is going to take some, well, I'll say x, and return some x. So it's a little, potentially verbose in Scala. And we have to have these manual type descriptions. In our language, we're going to have a way simpler syntax where you define the parameter with a backslash and then a letter, and then you have an arrow instead of an equal sign, and then the body goes in the right hand of that. So really, it's just the x equals x sort of thing. So I mean, you could write something like this in Scala, but it would have to be like that. And of course, that won't quite work because you need type parameters, and you cannot have so-called polymorphic lambdas in Scala 2 at least. So, but that's basically this first thing. So it's this function. Essentially, it takes one argument and will return that same argument unchanged. So that's what's called a lambda. And happy to give it a different name if you would like to recommend anything. For now, I think it's in the term. It's called lamb. Maybe I could even. I don't really love. I was kind of just, as I mentioned, I don't love the unnecessary concision. I'll just go with lambda. And then maybe I can keep this application or something, or apply. But we can talk about other names for these things. So what is that app thing? So this is our lambda term. What is app? Well, let's make another example here. So application. So let's say we have that lambda right here of x to x. So let's go x to x. Well, now I can apply something to it. The way application is parsed in languages like Haskell, and that's kind of where the syntax is coming from. It's a little weirder than what we're used to. Usually application would be if I sort of called my identity function, I would take identity and call it with parentheses. But in these sorts of languages, these Lambda calculus languages, you just use white space for application. So it's really sort of just almost like a infix syntax, except with only one argument. So really these things are the same. So what this is down here is it's going to be a lambda to applied to this number 10. So we're basically going to call this function with 10. And if we were to evaluate this, we would just basically get back the number 10, right? Because 10 would be substituted in here, and then x is 10, and therefore we just get 10 back. So that's application. That's our second sort of primitive construct. And then obviously we have these variables. So in here I'm referring to a variable, and then I have my literals like int. I can also do stuff like if, then, else, and whatnot. So if true, then 10, else 20. That would also be another expression. So that would be just like calling identity with, if true, 10, else 20. So a bit of a stranger syntax. Let me actually write this as an expression, just so we can see what that is going to look like. So, or as a term literal. So I wrote parsers for this, by the way. Maybe I can actually print out what T1 looks like. So I didn't want to have us go through the pain of writing parsers. That would take too much time for what I want to go over today. Let me also make my console font larger. 24. So this is a lambda from variable x to variable x. So I think that makes sense, because a lambda basically has a variable that you're binding, and then it has some expression, which is another term that uses that variable. And in this case, the term happens to be just a variable, which is also a valid term in the language. So the whole expression that this is parsed into is a lambda that binds variable x and then simply returns variable x. Now, if I did the same thing by, let's actually, yes, say t, I'll make increment my numbers here for my other examples later on. Val t2. Let's see what this looks like. Oops, I'm just going to actually go with 10 for now. Hopefully this all parses, by the way. I might have to make some adjustments if it doesn't. Yep, okay, so now we have an apply node on the outside, which is basically taking our T1 here, our lambda, and applying the number 10 to it. So that's what that node is. And it will just get more or less complicated from there, right? I can also print parsing.parse of, let's just say, the number 10. That's a literal integer, or I have a literal Boolean, false and true. So I can have any combination of those. So if I instead just ignore the x and always return true, then this would be applying the number 10 to a lambda, which with a variable x, which just never used x internally and always returned true. Okay, let me know if you have any questions on the basics of that syntax, but that's basically the language we're working with here. It's very simple to start with. Okay, let me go to the Discord. Cool, nothing there. So the goal, I guess we have two goals. One, we can very quickly actually write a way to evaluate these terms. So we can take some term and turn it into a final value. So just as we have, where did I take my notes? Just as we have this infer function, we can also have an eval function, which will take our term and return some final value, as long as, of course, this term is well typed and makes sense. If this term isn't well typed, we might not be able to fully evaluate it. Maybe we could take a look at what that means really quickly as well. And let's think about this if then else syntax. So I have if some Boolean, then something else, then one thing, else another, so else 20. If true, then 10, else 20. But nothing is stopping us from writing if 50, then 10, else 20. And if we look at our syntax tree here, this might actually even parse. So I'll say print line, and I'll have Copilot hopefully figure that out for me. Come on, Copilot, you can figure it out. There we go. Oh, I have to parse it though. I'm just printing out the string parsers dot parse. Hopefully that parses. Yeah, it does parse. So it should not be the responsibility of our parser to figure out that the types line up. In fact, that could be really, really difficult to do. We want to sort of work in a pipeline that simplifies things, break things into a series of steps where generally first you have the raw string of your program, then you parse it into some kind of abstract syntax tree, which is in this case our term type. And then further from there, we can take that term and try to type it. So we can get back sort of a term with a type. And if we were able to do that successfully, then we know that we can probably evaluate that term and turn it into a value, or give the user some error messages that help them write a term that actually makes sense. But we could not evaluate this. We could not decide which branch to take based on the number 50, or we can come up with some arbitrary semantics like JavaScript has and treats any number that's not 0 as true. But that is a horrible thing to do, which is why only JavaScript does it. It would be very confusing. Because really, not any term can go in here. Some other complicated term, right? We could have another lambda that did something and was applied to something else. It would be very difficult to figure out just at the parsing stage whether or not this turned into a Boolean term. And yeah, so we definitely want the user to be able to put expressions here. So we wouldn't want to say, if I go back to our term, we wouldn't want to just say that if then else had to have a term, a literal Boolean here. That would be, I guess, possible if we wanted to restrict our language like that, but then the user can only use literal Booleans as their conditions, which is not very interesting at all. We want to be able to accept any term there, other computations that will evaluate to a Boolean. And using a type system, we can know at compile time the type that any term will evaluate to, at least for most cases. Okay, at least for well-typed terms. Okay, so our goal is to, I guess, first we'll implement an evaluator, because we don't necessarily, if we get a term that doesn't make sense, we'll just blow up at that point. And that will be a little simpler to do. We'll get more of a feel for our language. And then after we do that, we'll work on the much harder problem of inferring types for our terms. And just to give some sort of ideas beyond that is one thing we want to do with this language is allow for polymorphic lambdas. So this identity function in Scala has this type variable here. We want our language to have type variables. So if you write the term x to x, we want this to infer not as, a function from int to int, but a function between type variables that basically says, sometimes you'll see it written like this: for all a, we're going to take a to a. So what this means is basically you can call this function with any type. And if you call this with an int, well, then that a kind of gets hard-coded to int. Oops. So if we call this with an int, we'll get an int back. If we call it with a string, we'll get a string back, et cetera, which makes it very flexible. This code, this identity function, is very reusable. So that's a nice property to have. And the last thing that you can possibly tell about this language is that we're not explicitly giving types to terms. With this language, we can actually get full type inference. So we want this type inference to, in Scala, it's actually quite limited type inference. It's still better than Java, for instance, because we can still infer types based on the values of bodies. But one limitation of Scala, maybe it's a limitation, maybe it's not. Honestly, it doesn't bum me out too much. I don't really find myself sad about having to do this, but you do have to give the types of arguments. Here, in this language, in languages like Haskell, you actually don't, and it can figure out what the input needs to be based on how you use it. So if I were to have something like this, if x, then 10, else 20, well, we can use sort of our brains here to figure out, well, what type should x have based on how it's used? So, can anyone tell what we want the type of this lambda to be? Let me check Discord. Yeah, Boolean. Boolean to int, exactly. So even though nowhere did we specify Boolean here, you couldn't do this in Scala, unfortunately. But with this type inference system we're going to write with Hindley-Milner, it can figure out, based on its usage, what type of function this should be, and then propagate that elsewhere, which is yeah, Boolean, if not JavaScript, yes. And in this case, it's not. So let's go through this a little bit. So that'll be type A to A. So for all A, type A to A. I'll just do that for now. And then maybe to force ourselves in the future, I'll do T20. Well, let's go through the example of what I just wrote, which was X, if X, then 10, else 20. So hopefully we can eventually write our typer to give this a type of not that, but of Boolean to int. So this should be parsers.parse of that. And then later on, we'll try to give this a type and hopefully get back Boolean to int. And we want our parser to be very, very smart. So here's an example of another function potentially, which is the term would be going from X to Y to X. So it's a function that returns another function that discards that second argument, returning the first. This is sometimes known as Const. It's actually built into Scala as well. So I give this one argument, I give it another argument, and we just get back the first one always. We get back 10. True has nothing to do with the result. That second argument is thrown away. And if we look at the implementation in Scala, it's quite straightforward. There are two type variables. We accept one T of any type, one U of any type, and then we return the T. So we never use Y. We only use this value of X. So yeah. So we can also write methods like this, and we want our type system to be able to figure out that the type you get back is going to be whatever that first type is, which means if we later apply that to something, so maybe I'll say val T4 term equals, let's take that same term of X to Y to X and apply it to first a 10 and then a true, we would expect to get back an int. No, yes, an int. Or if we don't apply it to true, we should get back a any to int. We can literally apply anything to it. And we're only going to get back whatever we apply first. So true 10 will get us back a Boolean. And maybe I'll throw that parser in there for now. Hopefully this parses. Oh, it does not parse. I've probably screwed something up. So let's not worry about parsing that just yet. Maybe I can do it if I'm careful. My parser is not the greatest parser in the world. Okay, yeah, let's not worry about that. I can probably figure that out later, but I'll just comment it out for now. Cool. So more examples. Let us start implementing something. The first thing I would like to do is evaluation, because that should take just a moment. So we already talked about what this needs to be, which is going to be a function that's going to get us some final value. You could also think about it as maybe reducing the term in some way. So basically, if we have one of these functions x to x and we apply 10 to it, well, then we can just get the smaller term, which is 10 here. But to make it a little easier and to solve some issues that would otherwise crop up, we're going to actually create another type called value, which is actually going to more accurately describe what we want to do here. So a value is going to be sort of a subset of terms. This is going to be the final evaluated term here. So we never just want to end with a variable. Variables should only sort of exist because they were introduced in previous lambdas. So we never want to end with a variable. Okay, and then we also basically want to be able to end with ints and booleans, but we could also end with a lambda, of course. So we're sort of gonna have that mirror where either we get a literal value or we have a lambda, because it could have been a top level lambda, and we're gonna actually give that a different name. We're going to call that a closure because of some details which we can see. It's relatively simple, but basically our final resulting lambda could have context that was sort of gathered along the way, right? A closure can close over variables that were introduced beforehand. As a quick example, if I have the function like this, xy10 or xyx, And if I apply this function to just the number 10, well, then the only thing I can do is sort of peel off the head here and replace it with this. So I'm going to get back this lambda of x10. So this will now contain within it the number 10. Maybe it also involved adding to this. Maybe it was this add method. So it's very important that we sort of keep this context around here. And that's basically what a closure is going to do. It's going to track the fact that this x that exists inside of this body was set to 10. So a little bit of a detail, but nonetheless, kind of important and awkward to implement correctly if you don't have this separate representation. We'll take a look. So a value is either going to be a literal int. So an int extends value. Maybe I'll say value int, v int, value bool. We're going to have a Boolean, which extends value. And then we're going to have ourselves this type called a closure, which hopefully can get figured out here, which is going to contain one of these variables from our term. So it's almost like, it's just like a lambda. Let me copy the definition of lambda. It's just like a lambda, except we're also keeping track of some kind of environment. We're going to need some type in our evaluation that's going to be called environment. And I'll just define that now, which is basically going to be a map from variables to other values. So basically, terms that we have already calculated would be stored in there. So the closure is going to literally close over the environment, aka copy a bunch of the environment that it would need to correctly evaluate its body later on. And the example I gave was what we looked at just a moment ago, which is this. So if our term is this function that's basically add that takes first the x, then the y, and then x plus y is the body. Well, if we only apply that to the number 10, then we're only going to get back this this method where one of the numbers inside of here is set to 10. But because it would be awkward to sort of go into that body and evaluate it, but skip the y, technically you could do that. It'd be pretty tricky and weird. So creating this closure ends up making the code a lot simpler, even though it's a bit of a weird concept. We'll see how it's used in a moment. But this is what we're targeting for our evaluation. Okay, so let's get started. So def eval. So what do we need? We need ourselves some kind of environment, which is this thing. And also we need ourselves a term. So maybe I'll go term first. So term, environment, and we're going to get back a value. And of course we could fail and we'll just throw in the case that something doesn't make sense, if this term is wacky. So I'm going to start by matching on the term and then we'll just work through these cases. Let me check Discord. Lean in. Nice. Okay, cool. Just going to take a sip. Let me know if anything I'm saying is totally insane or crazy, or you'd like a clarification. Try to give some more examples. Okay, so the first case, if we have a variable, well, we can't really evaluate it further. The only thing we can do is look inside of our environment and try to get it out of there. So I'm going to, in our environment, make a method called apply. That's just going to access the value in the map and fail otherwise. So maybe I'll say get or else, and I'll say throw new, and then hopefully, could not find a variable. So I'll make it a partial function just for ease of writing right now. So the only thing we're going to do is look up that variable. So I'll change that to a typed pattern and just look up in the environment that variable. It's hard to name variable because I either have to call it, like, for my own OCD purposes, variable, which is very long, or just v. So I guess I'll just go with v for now. Okay. So there we go. That's one down. Pretty easy. Apply is a little weirder, so let's skip that for now. Lambda, this is where we have our closure type. So I'm going to say closure, and maybe I'll just import all of value for now, or yeah, import value in here. So what we're going to do is we're going to just take the variable, take the term, the body, and then we need the environment. So we'll just close over our current environment, whatever that means. So that's really all we have to do there. And now let's go back to apply, now that we know that we're turning our lambdas into these closures, and we'll see why that's important. Because basically we have these two pieces, both of which can be expressions. We have basically the body of our function, which might be any kind of complicated term, but it should eventually be a lambda for this to be well typed. If you call something, the left-hand side really does have to eventually be a function, aka a lambda, which we know we're turning into a closure in this case. So what we could do is we can say val closure, and then we can sort of get its variable, its expression, and then its sort of environment in here by just simply calling eval on that first term, passing in our environment. So we're going to sort of pattern match on that. And so now we have the body, the variable and the term of that by evaluating this. But we also most critically have any environment that was captured along the way to generating that final closure, which if we did not have this step, we might have lost some information and it wouldn't make sense to say just return a lambda. So if you're just going from term to term here, it would have to return a lambda, which would be not enough information to evaluate that lambda's body potentially. We would have thrown away some intermediate context that could have been important. So you need to have something like a closure when evaluating it. At least that's what I found. Maybe there are other ways of doing this, but this seemed to solve this problem quite neatly. Okay, so now we have all that. So what can we do next? Well, now we have basically this, this is a closure. So it's something like this. So we have some variable that's bound to some expression. And basically we're calling it with E2, this other expression, this other term. So in order to make sense of this body in here, we need to get the result of this term. So let's do that. And I'll say, I don't know, value, maybe I should give this a better name. So maybe I'll call this X so it makes sense. And then I'll call this, V for now, for the result of expression 2. So I'll say eval expression 2 with the same environment as before. And now we can finally call this internal environment. So I can say eval E. And while this compiles, this is actually where we need to make use of this whole binding. Because basically what it means to evaluate a lambda like this is we need to evaluate the body, but let's go back to our other case before where it's x, y, x plus y. So if we applied 10 to this, right? Now we can't just throw away this knowledge that we know that x is equal to 10. We need to evaluate the body of y while knowing that x is equal to 10. We've added that information there. So basically the way to do this is to take our environment and so-called extend it, adding the knowledge that x is equal to this result value. So x is going to be whatever the right-hand side expression is in this context. And that's exactly what we're doing. So we've evaluated this right-hand side, getting this v part here. And then before we evaluate this thing, we need to know that x in here is equal to that. So we're going to extend the environment, telling it that this variable is equal to that value. But of course, that method doesn't exist. It's quite trivial to write. And we're just simply going to say, map and add that one thing and wrap it up in this little helpful wrapper type that we have. So we're just going to add to the map essentially. Hopefully that makes sense. Little details. And also I'm spending a good deal of time on this stuff. And of course, there could have been some environment that was added internally that was lost. So that's where we need to also add to this. We need to sort of combine. So let's also create a method on this, which will simply just combine those maps. So that's where we need that other map that was introduced in the closure. It can be a little complicated, but it's very necessary. Otherwise, we'll throw away information and things will break when we don't expect it to. Beyond that, it's slightly straightforward. Let's see this. So basically here, we want to first evaluate this conditional, right? So this, and we know as well, this should be a literal term dot Oh, valt. Where's my term? Literal dot. What was it called again? Literal. Oh, just literal dot. It's in term literal dot l bool. Okay, just getting some weird term dot literal dot l bool equals evaluating the conditional with the environment. And it should know that bool is a Boolean. Okay, cool. It's just because of the weird typing. Is it sad about this? Cannot be extended, acquired. Oh, it's a value. Duh. This should get back a vbool. I knew that. So that's a weird thing with these two different types. But that condition is a term which really only makes sense to eventually be evaluated to a Boolean. Otherwise, this expression is not well typed. So we can unsafely pattern match on this, which would throw an error until we have type inference, in which we would have previously ensured that this was not the case. But for now, we can just sort of blow up at runtime, if you will. Okay. And then based on that, we can say if bool is one thing, we can do basically evaluating the then branch, the true branch with the environment. Else, we evaluate the false branch or the else branch with the environment. So we're just kind of reusing our own language constructs to interpret our little DSL here. And then a literal is quite straightforward. We can just match on this literal. And if it's an int, we'll just package it back up in its value equivalent. And that's really all there is to evaluating. And we'll see if we got that correct. So let us print the result of evaluating. I'm going to make another helper function called just eval, I guess. I'll just call it eval here, where I delegate to the other eval, passing in an empty environment. So I'm just going to make an empty environment just so we can call that a little more tersely here. So let's see what that gets us. Should get us a closure. And it indeed does get us a closure without any context in there. Cool. So that's one thing. Let's see what this is going to be. It's eval t2, which I think should be, yeah, the Boolean true. Huzzah. That's pretty great. And then let's see what this is going to be. I think this is going to be another closure. Yep, this time a variable x, which is an if then else inside of it, because it's basically unresolved. Now, if I called this, we should get either 10 or 20. So let us call this with first true. Hopefully this works. And we get 10. And if I call it with false, we should get 20. And we do, we get 20. That's that result there. So it seems to be working just fine. Okay, and I think, well, this is the same exact case. Oops. X, whatever. too many numbers, not what sure I've used so far. I don't think I've used 100. So yeah, oops. I don't know what I just did. Whoa, what did I just do? This was just working a second ago. Oh, is this the one that didn't make any sense? This is the one that didn't make any sense. Yes, of course. So this should fail. That makes sense because I'm trying to match on the integer as a Boolean. So you evaluate without checking if well typed before. Right now we're doing that. We're going to add the typing in a moment, and then obviously usually you should check if it types first. So now we're just going to blow up at runtime because this is now not a typed language essentially. Are the normal rules of lexical scopes evaluated as expected? Because if the closure sets x inside of the end, and then the lambda uses x as well, it gets added twice. So that's a good point. I might have it backwards then. So we should see exactly what should go where. It would be good to test that. I might just ignore it for now. But if we can think of some particular, if you can think of a test that should blow up, we could try to run it with both and then fix it. Because yeah, there are some details, which is basically, yeah, should env come first? Should I extend? Am I extending the right environment here? I'm guessing you're probably right that we don't care about the original environment because what are we evaluating? We're evaluating the first expression. No, because that one is also inside of this environment. So I think we need the sum of both environments. Now, which one should be replaced? I'm not sure. Also, which one should take precedence? Yeah, you're right. I think maybe I need to extend X on this side. There are a few different variations, but I'm not really sure how to force an error. So this is definitely a tricky place. Could be bugs. To do, flush out bugs, write some tests. There are a few places where that can happen. But yeah, other than that, we've basically implemented evaluation for this simple language. And it's relatively straightforward with that one wrinkle about the closure and adding, passing the right environment along, which is basically which variables were bound, and they're bound by function applications. So when we apply this to this, we need to know that X is equal to the result of this. And that's what that environment stores for that subtree, for at least the body here. Okay, but now a step up. Let us think about the world of types. Okay. Am I in my little infer file? I am. So let us make ourselves a type. So usually, when we're writing a typed programming language, we kind of interact with types in this weird way where we can't really get our hands on them. We can use them in type descriptions, but once again, they don't exist at runtime. And we can kind of play with them, especially with the language like Scala. With implicits, we can sort of encourage them along, but it's like we're sort of, balancing like a little dust mote in the air on our hands. We can't really just grab it and do what we want with it. We sort of have to coax it along. It feels a little ephemeral to this higher world. But when you're implementing a typed language, you, of course, need to represent types as terms. So because we're writing our own language, we're going to make a seal trait called type, and we can do anything we want with these types when we're basically trying to model the domain of type systems. So now types are our values. So we can get a sense of we can demystify a little bit of how this process works, a little bit at least. Once again, we're not implementing the Scala type system, we're implementing this type system known as Hindley-Milner, which is for basically being able to fully infer this sort of basic variation of a lambda calculus with some constraints. But in a sense, it's more powerful than Scala's type system because we don't, at least the inference part, because we can fully infer things just based on their usage. We don't need to ascribe the types of parameters to functions. It can figure it out based on its usage. Of course, we do not have subtyping. So one of the reasons why Scala has this is it would be very wacky and insane to have both full type inference and subtyping. And because we're running on the JVM and interacting with Java, we need subtyping. And so we can get rid of this full type inference, which honestly I think is fine. I guess if you really adore that, it's nice to have it. But generally in Haskell programs, you end up adding the type annotations to everything. Anyway, it's just good documentation. But it's cool to still learn about. Great. So now we have to think of what is a type. And so we're really going to have a few types that we want to deal with. Maybe we can look at some of our examples. One, we have this example. So we have these sort of type constructors, these concrete types, like bool and int, which are really just these identifiers. And so if your term was an int, it's going to have type int. If it was a Boolean, it's going to have type bool. So we can start with that. And generally that's called something like, I'm not sure if honestly tcon stands for type constructor or type constant. I think it's type constructor. I don't know, but we'll just call it tcon for now, because that's what I've seen it named in the past. So that's like something like bool or int or string, right? One of these. It's just a name for a type. And then, of course, we have things like this, bool to int. So we've taken our type constructors, but combined them in this way. And generally, this is known as a type arrow, but it's basically a function type or an arrow type. And it basically, we usually write it in infix notation, but it's really just this thing that has a from type and then a to type. So type 1 will be a type and type 2 will be a type. Great. So that's the other case we need. Now, of course, we also have, as we've seen, functions like this, x to x. That's sort of the term. And the type of this, well, we don't know anything about X, and we want our language to be polymorphic. We want to be able to write these terms without sort of specifying. If we were forced to, we could say, well, X is an int, and then we would know that this is sort of monomorphic is the term for this, where every type is a concrete type like that. But we don't want to have to specify or constrain our functions to just work on a single concrete type. We want them to work on any types. So for all A, we want to be able to have a function from A to A. And that's called, polymorphism. And so in order to achieve this, one of the things that we'll need is a type variable. And that's what this is going to represent. Extends type. Okay, I'm just going to check the Discord, see some typing. I'll check back in a moment. Okay, but that's basically the beginning of what we need. And I think we could probably get through everything we need today with this. And I'll sort of talk about, things get a little more complicated, and why it took me a few times bashing my head against other implementations is because there are some other details that are required a little later on, but sort of having to absorb everything at once made it very difficult to figure out what was actually important and what was and what was just sort of solving for some eventual edge case. So this should get us far enough for now, and then we'll talk about the limitations a little later on. Yeah, so that's true. So type constructors are for generic. Yeah, maybe it's for type constant. I know that this, in the implementations I looked at, these things were generally called, it's Haskell. People love abbreviations, right? So instead of Lambda, it was just lamb. Instead of application, it was just app. So I don't really know what con stands for. Maybe it's for concrete type. Maybe it's for type constructor, but yes, usually you'd think of something like a list being a type constructor because you need to apply it to some other type before it becomes a real type. But we're not dealing with these kinds of type constructors in this language. So maybe we'll just think of that as a concrete type for now. Not really sure. I should check out that Wikipedia page for a better name or something. But yeah, if anyone knows the right terminology for something like an int or bool, that's great. And I'll just keep my examples here as a var. So that would just be something like A. So this could be A to bool, for instance. Okay, great. And we're going to need to maybe make some additions here, but let's just start. Once again, let's start and not worry about all the things we'll need, and just try to work through this and add things as we go along. So let us write infer. And we want to basically take a term and get back a type. Now, we already said this might fail, but in that case, so be it, we'll just blow up. So we won't worry about even writing option here. We'll just explode, keep things a little, get more on the screen at once without dealing with for comprehensions or getting or elsing or anything like that. I don't think we'll need to do any try catches, so we'll just fail fast if we run into some issues here. Okay, so let's match once again on our terms and look at the full language. We'll ignore some things like if and else for now. Maybe we'll start with just literal, because this one should be actually pretty straightforward. We don't really need anything else. If it's an int, we want to make our type an int. And if it's a Boolean, we want to make our type a Boolean. That's really it. If we wanted to, we could sort of pull these up and put them in here and say, val int type. Maybe I'll do that. Val bool type. So now we have these there. So I can't accidentally come up with slightly different ints. Type dot bool type. Cool. And I really could just have these hard-coded as well instead of type constructor, because this is not user extensible at the moment. Right now, we only have these two types. Great. So we'll add those. And these are, the types. I'll widen that. Okay. So that's super obvious and super simple. And we can just try to even use this right now by printing. Let's first get a term, bool term. So parsers.parse of, let's just say true. And then I'm going to print the result of typing that. So I'll say infer, and then also int term. Try to use, there we go, int term. Print line. Cool. So hopefully we should get true. Oh, something blew up. Oh yeah, where is this happening? Exception match error. Oh, it's still, I still have my faulty case of the 50. Yeah, we're not gonna do the thing that blows up. Where did 50 go? There we go. We're not going to evaluate that. That doesn't make any sense. But we'll keep this around so maybe we could try to see that it fails to type as well later on. But we're not going to try to apply it. Okay, let's see. Back here, nothing should be failing so far. Yeah, there we go. And maybe I'll also remove some of the others print lines as we have enough to worry about. Cool. So yeah, yay, we have a bool type and an int type. Straightforward, amazing. Great. Okay, let's keep going. For a variable, that's going to be a little interesting. So we're going to have this kind of type variable here. Convert to type pattern. And so really, if we have a variable, we should, if we look at how it was used previously in our evaluator, it should have basically always been, it should be known at this point. Because it should have only been introduced by a lambda that was sort of above it in scope, which means we can kind of treat it the same way in our inferer as well. We similarly need some kind of type context, some kind of typing context for us to look up the value, the type that was previously given to this variable. So I will make another type here called maybe context. I think the other one I had end, and now I'll have context. And this is going to be similar, but it's going to be a map from variables to types instead. So those term variables to types. And so I'm also going to have this accept one of these type contexts. And we can also give this a nice little apply message. Let's see. I'll let Copilot help me out here. Yeah, and it'll be smart. Variable not found. So we'll just look that up in our context. So that's pretty trivial as well. Okay. I'm going to check the Discord. Did it start an hour early? I think last week we shoved it back an hour. But don't worry. Oh, daylight savings time. Yeah. Did I start early? I might have started early. Apologies. I didn't realize Europe had its own daylight savings time. Luckily, we haven't gotten terribly far, and we have sort of just started our type inference. We kind of looked at the language, but I think you'll be able to catch up, Naveed. But let me know if you have any specific questions. Just to sort of quickly recap for anyone just joining us. We have a term in our language, this expression type, this abstract syntax tree, which is basically some kind of variable. We have lambdas. We actually don't have addition, but you can call lambdas with arguments. And then we just have ints, Booleans, and if then else's. But that's really our whole language. So a very trivial language. We've implemented a possibly buggy evaluator. It seems to work with our examples, but there's some skepticism. It needs some more test cases. And now we're working on a way of getting types from our terms. So type inference. We have fully untyped lambdas. You just have something like x to x, and we want this to infer a type of something like a to a, some type variable. So we're turning that unbound or sort of this constraint list variable into a type variable. So for all a to a. Anyway, hopefully it'll make sense. And we're just starting with the basics first. So if you have a literal, the type of an int is going to be the int type. The type of a bool is going to be a bool type. The type of a variable, we're going to have to look into our context, some context that we've passed around, which is a map of variables to types. Okay. And now it's going to get a little wackier. Maybe let's start with, I'm not really sure which one's easier to start with. Maybe first we'll start with lambdas. So we have a variable, maybe I'll call it x in this case, because the v is throwing me off because there's value as well. And then we have some kind of body. So we know one thing though, the type of a lambda should be something like a to b, right? It should be something of that shape. We kind of know that we want to get back a type arrow. And unfortunately, we don't necessarily know just yet what either of these are, right? It depends what it is. If it's something like if X, then 10, else 20, we might be able to infer in our body that X should actually be a Boolean. But if we don't look in our body, we don't really know anything about X. Maybe we can see by what's passed in, but we sort of have to determine how it's used to figure out what that X should be. So clearly, this is going to sort of complicate our algorithm eventually, where the way we evaluate the body is maybe going to give us information about the X. So in this case, we can't just know, we don't know anything about X right now. It's totally abstract. So we don't know anything. And the body is kind of going to be the result of inferring the body, right? So that's the body type with some context. Of course, that context needs to be extended once again by this X, right? Because we cannot really figure out the type of this body because it's going to refer to an X. So it's eventually going to look that up here in this case. And if it's not in the context, it's going to explode. But we don't know anything about X. So this sort of this weird bidirectional constraint where to figure out what X should be, we need to see the context it's used in. But then when trying to figure out how the context uses X, it's going to try to figure out what X was, and it will blow up. So we have this kind of recursive weird issue. One hand, washing the other. Ouroboros. So this is going to sort of force us to complicate things. But for now, we'll solve a couple of problems. One is we need to extend this context by something. So I need to first make some method extend. And I basically need to say that this variable X is equal to some type. What should that type be? Well, this is why we have type variables. It's one of the reasons why we have type variables. We can create a new type variable, which is basically sometimes referred to also as a meta variable in this context, which is really just a placeholder to tell us, we don't know what the heck X is. Let's just give it some identifier, some unique identifier, and we can figure out later some stuff. But that's just going to save us in this case. It's going to give us a value in there so it doesn't explode. And to do that, we're going to sort of make a new type variable. So I'm going to say type tvar, and maybe I'll make a method called fresh here. And we're going to do something very evil right now because I don't feel like making a state monad. I don't feel like I probably would use, something like Zio and a ref for this, but just to keep things simple, we're going to have ourselves a current character, which is going to start out as A, and we're going to get ourselves back a new type variable. And we're going to do this by saying tvar of the character to string, and then I will say car equals car plus 1. Plus, let me say car plus, is that sad? Car plus 1. That should work. Oh, that's an int, and I have to say .to car. And then I'll say val result. So kind of hacky, but it'll do the job. So we have this private car, and we'll just do this for now. Coming up with a random letter. Obviously, this is only going to get us some weird letters after we exhaust the alphabet, but for these purposes, this is totally going to suffice. And now we can take this type variable and just assign it to X. Now we have to make this extend method, which simply is going to, let me import tvar, because we're going to use that a lot. We're just basically going to add that to our map. So just the same as how we had an environment during evaluation, which was a map from vars to values. Now we have a map from vars to types to help us in inference. Cool. But now, so yeah, basically it's going to be a function from some type to something else. And maybe we could just see what the heck this is doing so far. Let's define a lambda and figure it out. Of course, okay, now we need infer. Might make another method because I want to be careful here to make sure I always have to pass this around. So I'm going to call infer term context.empty. The reason why I'm making another method is because I don't want to overload this, because we still have a lot to do in here. I don't want to accidentally call one that adds an empty context. One of the problems with default arguments is it doesn't really save you when implementing a method body. So I'd rather be forced to string along the context everywhere and make sure I pass the right context rather than accidentally forget to, and then now I have an empty context in one of the branches. So one of the perils of overloading is that it can make it rewriting methods a little tricky. Cool. All right, so let's make a method called empty and then just have an empty context, and that could just be eval. Okay, so now back here, I'm going to, where are we calling infer? There we go. So I'm going to change both of these to infer top. So we don't have to do anything. And then I'll make another term, a lambda term, basic lambda term. Let's see what it parses out for us. Okay, I might even make it simpler than that. Let's do this. So what is the type of this lambda term? No, it blew up. Did it blow up? Variable not found X. Okay, that's super interesting. I would have thought it could find that. Oh no, it probably couldn't. Let's see why. So, okay, so it says it could not find the variable X, which was in here, which is when we're inferring the body there. Yes. But I was saying that I called this with X being equal to this new type variable, so it really should have been in there. I must have screwed something up. Let's see if I can trace back what's going on. Var type, which is called there, which is called there. Huh. Oh, that's because this isn't a real lambda. I wrote something incorrect. It's not a lambda. Okay, it was parsing it as just a variable, and then there we go. So now it's this array from A to A, essentially. So it's a function from A to A. That's what I actually want. And we can write a pretty printer for these types if we'd like to, but for now, this will do. Or actually, let's see. Maybe I can do that. So self def. I'll just increment override to string, I suppose. Self match. So name, and then we will go with T1 to T2. Cool. And this will obviously suffice for now. We need to worry about in the future of if there's a function on the left-hand side, how to deal with that. Basically, I would deal with that like this, which is some sort of, with parens, basically make another variation of it like this, and call with parens on one side, on the left-hand side, in case that happens to be a function type. So kind of a hacky way of doing that. And that's not overridden. So yeah, maybe since I have done that, I'll just do that. Okay, so these two functions. Now, hopefully it two strings it a little more nicely. I'm going to check Discord in a moment. After those look okay. So yeah, there's bool A and A2A. Perfect. Great. Okay. So we're getting some basic types, but there are definitely going to be some limitations as well. Let's see what happens if we do something like 12, right? That should be okay. Okay, so we even get A2 int, which is pretty nice. And what if we do something like, X, Y to X? Let's try that. So we even get A to B to A. That's kind of cool. And let's do 12, etc. A to B to int. Okay, great. So everything seems to be working just fine so far. Yeah, so really the thing that we want to move to, though, is especially this if then else case. And then we can just sort of force ourselves to think a little more creatively before then, because there is that case where we use it like this. So we haven't implemented if then else yet, because that's going to be a little trickier. But if we imagine what's happening here, which is that, okay, what if the usage of X is going to tell us something about this function? Say this was a top level definition, right? Some sort of my function equals this. Well, we should be able to figure out, we have no other information, that this is indeed a function from Boolean to int. But currently it's going to, if we were to run this, it would say it's some A to int, which is not correct. This could not just accept anything. It has to be Boolean to int. But if we look at what's happening here, we're clearly just going to return some fresh type variable as the first argument of our function. The body could be something more interesting than that, but here we're not going to take that knowledge. So the important insight, and basically how Hindley-Milner the actual algorithm that we're about to get to works is you're going to gain some kind of knowledge from typing. So it's kind of like when you write a parsing algorithm, perhaps, where if you want to be able to parse right to left, some string and then some number, and you want to be able to first get out the string, some string, and then get the number, you can't just have a parser that takes a string and returns, some type of a, like either a string or an int, because that's not going to be enough information to tell you where to start parsing the next bit of information. So generally a parser would also need to return some kind of, where it stopped parsing or the rest of the string, such that the next parser could pick up from there with the leftovers. So it's a little different, obviously, but we're going to have to enhance this infer method to not just return a type, because that's good to know. It's good to know the type of the body that we know that's going to be int. That's great. But we also learned something about what x has to be. We have this new constraint on x. And now we can use that constraint to basically figure out what it needs to be here. But how do we do that? Furthermore, if this were a little more complicated, let's say this were some other kind of, let's say we had some other kind of function that we accepted in, some function f, and then an x. Well, what if we called f with a 10 in one place and then f with a string in another? Well, we would probably have to, blow up, right? There are no subtypes. So we need to know that, oh, well, in this case, f was being called with an int. Therefore, we're thinking that f is a function from some type into something else. And then also it's called with a different type here. So we might learn something in one of these branches that we then want to be able to unify with information from other branches to tell us if what we're doing even makes sense or not. So there's this idea of sort of being able to get information back from the typing when we type some sub-expression, which we can apply to other paths of the sub-expression. We're basically just gathering up knowledge, gathering up information as we go along. And there are sort of two concepts that we're going to introduce. One, we're going to make this method called unify that tends to exist. And basically this takes two types. Let me write it up here. So def unify is going to take two types and then get us back some kind of knowledge. So some kind of knowledge about how they relate. This knowledge is generally called to referred to as a substitution, but that's I kind of want to use the word knowledge for now, or info. It's knowledge that we can apply to change things, to make things more similar. But let's look at an example of what this needs to be. So, okay. So yeah, basically, if we have two types, and one is a type variable, and I'll just use some symbol here, dot, and one is an int here, what we want to get back out is, well, that a is actually int. So we're unifying a and int. Basically what we're saying is these two types should be the same thing. And if they're not, if they're clearly not, if it's something like Boolean and int, well, then we actually want to boom. We want to blow up. That does not make sense. But because we have some like wiggle room, we have these type variables, these pieces of these variables that we don't know anything about yet, and we're trying to constrain, well, then we can use these comparisons to constrain them. And so we basically want to get back this map, another map. This time, though, we want to go from type variables to concrete types. So the things that we don't know really in our system are all these type variables that are wandering around. And we're going to basically unify those with other types and then learn something about them. Also, if we unify two things that don't make sense, this is where the type algorithm is going to say, hey, these things aren't making sense. There's a type error here. You're trying to use something in this place that just doesn't make sense at all. These two things are not the same, but they should be. But if two things are not the same and one is flexible, then we can say, okay, well, now you're the same. And the useful part about this knowledge is that we can then apply it. So we can take this knowledge and apply it to one of our sides or both sides of our algorithm, which should then make it the same. So the whole goal is if you have type 2 and you unify that with another type, you're going to get back some knowledge. I'll call it K. And then once you apply that knowledge to both types, they should basically be equal to each other. That's sort of the way this works. Either it blows up or they should be equal to each other. So if it was a type variable A that you're unifying with Boolean, well, then we apply our knowledge to A, it's basically going to become Boolean because it's this map from A to Boolean. And likewise, if we apply it to a concrete type, it's just going to basically be the identity function. And so those are then the same. So it gets you back this piece of knowledge that then you can use to make those two sides equivalent. That's kind of the idea of this unification algorithm. And apparently it works in other domains as well. So this could be a useful algorithm for when you're trying to do this, something like a type system, something constraint solvy, when you have some rigidity and flexibility and you want to sort of let these constraints propagate around and help you figure out what something is based on how it's being used. So let's think about how to apply that then. So we have a type here. How can we apply this? And we want to basically get back a type. Well, let's match on our types. So if it's a type constructor or a constant type or something, let me convert to typed pattern. That's not going to change. That's set. If it's a type variable, well, then we need to see. Let's also convert to type variable. Either it's in our map, so get or else. We're going to get the type in that map, or we're just going to keep it the same, right? If it's the same, it's the same. So another example would be if you had two functions, one from A to B, and you're unifying that with the function A to int, well, then the knowledge you're going to get back from this is, well, B is actually an int. I know that B is an int. Maybe I'll write it like that. It's too many arrows. This is more of a saying that A is a Boolean. And now if I apply this piece of information to both sides, the B basically just turns into an int. So I get back these equal expressions, these equal types. So I've learned based on the positions of these functions, if these are two functions, then their types should be the same. And so I can learn from both ways. And maybe on one side, we know that it's string to B, and that should be the same as A to int. Therefore, we should get back this piece of knowledge that A is equal to string, B is equal to int, apply it to both sides, and we get back the same functions. So now how do we deal with this type arrow? Well, we want to basically get back a type arrow. We just kind of want to traverse, really, which is quite simple. We just apply to both sides. And that's basically everything we need to do. Okay, I'm going to check the, okay. Regarding, so yeah, I guess that's a good point with this. So it depends on, I guess, where F is introduced. And maybe that was a bad example. I was kind of realizing as I was talking about it. There are some issues I know with that I was reading in the Wikipedia article and elsewhere, which is that technically you cannot have these for all methods if they are not introduced at the top level. There is some undecidability with the polymorphic Lambda calculus. So we need basically to have, that's why languages like Haskell have let constraints, which would be something like let x is x, and then you could use it. But if you do something apparently like instead a lambda that is accepted here, and then you say, if true, then ID 10, else ID 20, you can't actually, I don't believe, write something like that, at least according to the Wikipedia article. I thought you could do something like that with Haskell, but apparently you instead would have to do something like that, at least according to Wikipedia. Anyway, it's a bit of a detail, but maybe there are some constraints there. But we can talk a little bit more later about what one of the difficulties of this is. I can at least see in what we're going to implement that it wouldn't work out, and why we do need to complicate things. There's this one thing I'm leaving out, which is necessary for basically writing some kind of code like this, to have these sort of bindings, and to have these sort of fully polymorphic functions. Okay. So let us see. I'm going to check back Discord. Yeah, there's probably some weird restriction somewhere. Okay, but let's see how far we can get. I think we can get to the end. We might go over a little bit. I mean, obviously, we're back to the traditional Zymposium time of like an hour and a half, but maybe we'll go a little further just because I want to get to the end. And I think we're close-ish. So the really key idea is that we have this piece of knowledge, and this piece of knowledge is sometimes known as a substitution, or sometimes subst, because everyone likes to make things too terse. And it's a little weird because it's this piece of knowledge, really. It's this map from type variables to types, but we're then using it to substitute type variables later. So it just depends on how you want to think about it. I kind of like thinking about it as it's this piece of knowledge that you have acquired by attempting to unify two types, but then you can use it to substitute one of the two sides. I'm just going to stick with knowledge for now, but if you hate me and you hate that name, let me know, and we can change it back to substitution or something. Okay, and now we can actually implement unify. So we have some examples here. Let's take a look. Well, I love pattern matching so much. It's just the best. So we're going to pattern match on both types. Now we can start to think about what the different cases are here. So we have maybe type variables. So we'll definitely have type variables, and I'll just import that directly. Name one, or maybe I'll just do this. tv1 is a type variable, and tv2 is a type variable. If they are the same, if tv1 is equal to tv2, then we've learned nothing. They are just the same. Great. So we'll make ourselves keep saying it should be val. I'll just make an empty map again. So we have all these different maps. Where'd unify go? Unify, there we go. So yeah, they're the same. We've learned nothing. If they are different, which we now know by matching, if one is a type variable and the other one is really anything else, then we know that tv1 is basically set to t2. I could make another nicer constructor for knowledge, but for now I'll just do the math there. So tv1 is going to be t2 because once again these are the same. So that's the example of a unify int, or int unify a. There is one case that you'll see handled, which is basically if you have a type variable that you're unifying with something maybe like an arrow, and the type on the right-hand side. So this would currently match this case, right? Where you have a type variable and then some other type, which happens to be an arrow, and that arrow contains that same type variable. That should be boom. That should be, there's this thing called an occurs check. Basically, you just make sure that this type variable does not occur in the right-hand side. We can add that later. We don't have a little helper method to do it, but we can also kind of avoid it. But that's why writing these things kind of takes a little, you can sort of lose the needle. I found myself losing the thread or the needle or both, just because there are all of these little, you also need this, which then requires these other things. So to implement the occurs check, we need a method called for getting the free type variables. So the free type variables inside of an expression or inside of a type, I mean. And it's all trivial stuff, but it'll take us off the path. So for now, we're just going to ignore it. I don't think we'll get into that situation, and we can fix it later. So to do add occurs check. But I hope that makes sense. That would be weird because basically it would create some crazy infinite type and it wouldn't really make sense. Should not exist. So it should be an error. Okay. Okay, and then same, we have the other way around, which is we have T1 with TV1. So let's just throw that in there. It's the same thing by the other side, and both would need occurs checks. And then we have the case where both are type arrows. So we had, where was that example? Up here, right? So basically, we just want to collect the information from both sides and just kind of recurse. So we have, let's just say A to B, type arrow from C to D. And then we basically want to say, well, unify types A and C, those should be the same. And then add that information to val results, whatever, knowledge one. And then we also want to say unify B and D. and then kind of return a concatenation of both pieces of knowledge. Cool. Yeah. There's actually basically we're eventually going to want to make it right now a method called compose, where you basically combine this knowledge together. Maybe I'll just call it plus plus and implement that. Yeah. So let's go through this. So I will say k2.map case .map case tvar and type. And basically we want to, for each of these, apply our knowledge to these types. And then ty, and then we want to add it to our map and then wrap it back up. So we're basically just combining. We want to make sure we don't lose any of the knowledge. So joining these maps, but also sort of normalizing it as we go. So if there was a piece of information in one side that was, yeah, we don't have sort of different stories on one side of the map. Though actually, now that I think about it, I think we could just probably combine it, because anything in this side would probably override it. So maybe that doesn't make any sense, but I think it could. Yes, it could, because it could be nested in a type. Anyway, this is where things get a little confusing, joining these pieces of knowledge together. But we have a way of composing these together. That's great. And then we're going to unify these. Of course, we might also be able to apply this knowledge to each of these types before we compose it, because we've gotten some information already. And I'm not sure that's necessary, because maybe our composition down here will take care of that, but it couldn't hurt. And just so I make sure I do everything right, I'm just going to keep attempting to normalize this knowledge and apply it to all the pieces of information. Chances are none of our examples will run into this, but this is where things can get a little tricky. Okay. So if it's none of those cases, basically, well, I guess if they're equal, we've already sort of dealt with that. I think if it's any other case, and we'll see what happens, maybe I'm forgetting something, we're just going to blow up. So if one side isn't, oh, no, of course, that's silly. Yeah, let's go if they are equal, it's fine, because they could both be type constructors. And I guess I could have also used this for this case, but let's be specific. Type constant, whatever we want to call it. T1, type constant. And T2 is type constant. And if those are the same, then we will, oops, what am I doing? We will also be happy. I might be forgetting a case, but if it's anything different, so if it's like int equals int unified Boolean, that should fall through and blow up. If it's something else that we haven't described, once we've added occurs checks, if there is an occurrence, then it should fall through and blow up. If you're trying to match an arrow with a concrete type, it should blow up, etc. So now we're basically going to compare two values that we know based on our algorithm should be the same type. And if they are, then we can get some knowledge out of that comparison, which we can then use for subsequent computations. So it both gets us knowledge, but it also helps us break if one of these invariants, basically whenever we call unify, we're saying we know these two types should be the same. So confirm that and maybe figure out some new knowledge based on the fact that we know these are identical, or explode. So it's this weird thing that's doing a bunch of stuff, and it's definitely probably the trickiest bit of Hindley-Milner, but pretty cool, and it kind of makes sense. Though there's some, I probably screwed something up in the concatenation of knowledge. Okay, so now we can come back to our infer, and we can say that instead of just returning a type, we want to return a type and knowledge that we got in the creation of that type. So for a literal, we get nothing. So we get empty knowledge and a result type. For a variable, we get, I believe, empty knowledge and a result type. In the Lambda, this is where things are going to get a little interesting. So we can sort of think about how we want this to work, or is it the apply that things get interesting? I forget. But now we can think about this. We need some kind of knowledge, val knowledge. First of all, now that we've called infer, we're going to get some knowledge back. So that's nice to know. Can we just return that? I don't think so. Not yet, at least. So we're going to infer. So yeah, let's talk about this concretely. We have some x. and we have some body. Let's pretend it's that, if X, then 10, else 20. So this is E, and this is X, and this is E. So the first thing to do is, well, when we evaluate E, we need to give it a value for X, and we know nothing about X yet. So we're going to come up with a fresh type variable and extend our context saying that, okay, X is this, for now, some unknown type A. And so we know that that's some unknown type A. One of those type variables, so it's flexible. So when we unify it, it's going to be nice and amenable to us. Okay. And then, based on doing that, we're going to get maybe some information. Hopefully, our implementation of if then else will tell us, we're basically going to say, okay, X, you better be a Boolean. So let's unify X with the Boolean here. If that isn't true, it's going to explode. If it is true, now we have some knowledge here that tells us that the type variable is a Boolean. So we need to apply this knowledge to that type variable, basically. And then the body type is going to, I think, maybe also need that knowledge applied to it. I'm not entirely sure. I'm going to apply the knowledge to everything. Applying knowledge is good. I might overdo it some. I'm assuming the body should already know that, but better safe than sorry. Okay, I'm going to check Discord again. Happy to do a Prolog interpreter too. It's way out of my depth. This is already sort of struggling with my depth, but we'll see. So this apply one is maybe one of the more interesting ones. I hope that one makes a little more sense. But let's think about this now. So we have some kind of expression on the left-hand side, which is maybe going to be, I'll just call it lambda again, because ideally it should be some kind of function. Maybe I'll call it f. And then we have some kind of, I'll go with e, some kind of expression, some kind of term on the right-hand side. Maybe I should have called term expression, but it's too late now. So let's think about some cases here. Basically, what can we do? Well, let's just start by calling infer on, the f with our current context. Does that make sense? So we're going to make maybe get some knowledge based on inferring that, and we have our type of function. So f type equals that. And I'll make some question marks down there. We could also get the type of our e here. Of course, we might have learned something about some other free variables, perhaps, from the context of f that will help us infer e. So one example of, okay, so maybe this is a lambda, but it's using something like y that was introduced above. And, I just really have let's just do y plus 10. We don't have addition in our language, but we should now know that y is equal to an int. Y has to be an int for this to make sense. And if then I pass along y here, if that's what I'm calling it with, well, I should know that y is an int at this point when evaluating the expression. So I can use the knowledge gained ahead of time for this. So I kind of also want to be able to apply knowledge to a context, which is currently not possible. So let's overload our knowledge to apply to a context. Getting another context, and this should be pretty trivial. Basically, we're just going to, I'll just let Copilot do it. We're going to map over all of the types in that context and just simply call the type version of applying it. So we're just applying to all the contexts, the types in our context. So yeah, context is a map from variables to type, and we're just going to translate those types. So pretty straightforward. So just a nice convenience there to be able to apply knowledge to context as well. Okay, so now we have our expression type. We have our some knowledge that we got. We have our function type. And what should the type? So the goal is to give us the type of. I think I might have screwed up something with this as well, but we'll come back to that in a minute. Let me make sure. So I'm saying that the body type should be that. Yeah, I think maybe lambda is fine. So it's a little bit of complication here. So we're saying that this should be a a function type? And if it's not, like what should FT be? Well, the way we can sort of make an assertion about what function type should be and maybe learn something about that function type would be to unify it. So we're going to say the function type really should be what? It should be some applying FTE. So, okay, let me think about this. So it's a little mind bendy. So function type should be whatever the type of E is to some result value that we don't quite, I guess, know yet. Potentially. Maybe we figured that out in here, but the function type should be essentially a type arrow. So a type arrow from our input type, which we now know about, to something else that we don't quite know about. So maybe this is where we need a new type variable called fresh, and I'll throw that in there. So that's going to be interesting, and that's going to get us back some more knowledge. So we're basically making this weird assertion that should teach us something. Like the thing that we don't know is, what does this function return? And the best way to figure that out is to basically make some comparison, try to unify whatever we learned from just merely evaluating the function body with the knowledge that we also gained from evaluating the input type. And potentially we can then learn what the output type is. And if so, this knowledge should basically get us that. And I might be screwing something up here because there are some details, but that's essentially the idea. Hopefully this works. I'll probably have to explore this some more offline, but let's just get to the very end of this idea. Okay, whew. I may have bitten off slightly more than I could chew. We'll see what happens. So basically, we now need to return the knowledge, which is going to be not only K3, but also basically all the sum of all the knowledge that we've gained along the way. Might also need to apply this knowledge to this function type, because we could have learned something there. Not entirely sure. And then the final type should basically be, I guess that I guess that function type with that knowledge applied to it, I think. There's a few different ways of doing this. I should probably look at my previous implementations and the source implementations. This is where it gets a little wild. Cool. Hopefully that works. Let's try it on something that I wrote already that doesn't have an if then else type. Unfortunately, most of these things do. Oops. Infer. Oh, now I have a pair of things here. Let's see what we get. Okay, so T1 plus. Oh, that's not the evaling of the type. So print line. Right under that, we will say infer top T1. Let Copilot do it. Copilot probably would do just fine here. Great. And well, we're going to start getting some weird types like C to C, just because of the fact that I have that that variable there inside of the type var. Maybe one way to, this is so hacky. Eventually you write a method, something like normalize, that would go through an expression and sort of start over from A's, so it doesn't start looking wild. But for now, I could just be super hacky and say typevar.char equals, I'll just reset it to A before I start to parse. Yay! So now it's looking okay again. And what we really do need is if then else, because that will help us figure out, that's kind of the only way of adding a constraint to a type that we have right now. So let's try to do if then else. And this one's the trickiest because it just has so many different parts that we sort of need to. And in fact, I might just, let's do it, Copilot, come on. Boom. So, so it gets a little tricky, but basically we need to, I'll just sort of walk through, hoping that it's the same. This looks like what I've done in the past and what the implementations that look like are, so I think it's okay. And generally you might start writing a helper function to thread around some of this boilerplate, because for other constructs you would have similar a similar shape to them. The fundamental ones are really sort of listed above. But basically, we need to infer the types of all three of our components: condition, then, else, etc. Then saying that basically the condition needs to be a Boolean, and maybe that'll fail. If the condition is not a Boolean, it's going to blow up. Or if we didn't know if this was a free variable, now guess what? This condition type is now a Boolean. And then we're saying that both the then branch and the else branch have to be the same. We're unifying them once again. And then we can just pick one of those two types, run the knowledge that we got from unifying them, and then return that with sort of the sum total of all the information we gathered along the way. It's a bit wild, but hopefully it works. Let's see. Let's go crazy. So this is the real test, I believe. And was this the one that we didn't get to eval, or did this eval correctly? No, this evaled correctly. So this is going to be a function, a closure, that should take a Boolean and return an int. We theoretically should have that information there. So let's see at the very end. Yes. Yes. Haha. So that's kind of cool. I'm a little scared because of all that stuff in between. I'm not sure if I screwed things up in here in any way, but it seems to, at least. Luckily, Copilot threaded the needle. The tricky thing is introducing these type variables. I think I might have added too much unification somewhere, or unnecessary unification. Once again, I'm applying the knowledge to everything. I'm unifying everything just in case I screw up. But it seems right to me for the most part. But yeah, it seems to have. Let's talk about what it did, which is we had some lambda here. We didn't know anything about, like, if we sort of walk through it, right? We don't know anything about x. Like, if we're just tracking our own knowledge, there's some type a, x, which is of some type variable a. We don't know anything about it. And then we slowly get to this case where we see this if then else. And we've unified in our if then else, we've unified the condition type with Boolean. So the condition type was this a type parameter, and we've unified that with Boolean. Therefore, we're getting basically back a map from a to Boolean. So now we know that. And we're returning that bit of knowledge to the end of the world, basically saying that we have this, that type there. And this works because now basically the body was what we evaluated, where we learned that piece of information. The body contained the if then else, where we learned that a was indeed a Boolean. So that's in that piece of knowledge that we gained. And then finally, we've taken that function type and applied the sum total of knowledge to it that included that K2 or whatever that, and we keep adding knowledge all the way, potentially too much. But now we know that A is a Boolean. We'd applied it to our whole function type. So now we know that it goes from bool to int. So kind of cool. I hope I didn't make any mistakes, but I probably did. But also I hope if you didn't know anything about Hindley-Milner, it gives you a little bit of guidance. There are more details. I don't think there's enough time to go over that today. Maybe I'll practice this some more, try to wrap my head around it some more, make sure I didn't screw up horribly. But I'm glad I didn't have to refer to anything except for, obviously, I took the suggestion for doing the Copilot. Yeah, no, Copilot is insane. We're all doomed. But I mean, I think part of why it works is because there are many implementations of Hindley-Milner on the internet. But how it, yeah, it's crazy, of course. But yeah, that's it, I think. Let me see if there are any last questions. Thank you. There's one last, as I mentioned, the things that I sort of hand waved away is there's this thing known as a type scheme. And let me just briefly explain where this algorithm goes wrong. But basically, one way of getting it to fail, actually, I think I have an example that I wrote ahead of time. Let's take a look at this. So once again, it's this example of ID, right? So where we have this function ID that goes from X to X. We say if true, then ID 10, else ID 20. And actually, let me think. Will this fail? This might not fail. I kind of forget. Let's see what happens. Parsers, no, infer top T5. There's some issue with this, I believe. Where do we go? Oh, int to int to int to c. Is that correct? Is that correct? If true, then ID. I would have thought that this would just be an int. I might be screwing up. Okay, that might be an issue with my implementation, actually. So I'm not sure. Maybe that's where it's falling apart. I think T5 is a little wacky. But nonetheless, there is one issue where it might, if you give it a function like this, basically the way these type variables work, if I want something like ID, and I wanted to say, use it in two different paths of my tree. So I have some function ID, and let's just pretend there's a much more complicated function like this. And I want to call it in one place with 10, and then somewhere else, one place with true. This should work because technically we want this to be polymorphic. But without this concept known as a type scheme, without generalizing this, it's not going to actually say something like for all x, or for all a to a. It's going to try to figure out what x is supposed to be. And through the unification, it will, the first time it sees that x, it's going to say, okay, well, x has to be an int. And then it will not allow you to call it later on with true. And so basically, when you start to want to define these top level definitions, you need to have this idea of one complication of types where you sort of store these variables that should remain free in an expression and not try to be unified through multiple uses. This thing called a scheme, which is essentially this for all a to a thing. So I can call this multiple times in multiple places, and basically the a is going to be a new type variable every time I call it. So if in one program I call ID 10 and ID true, it's going to not unify this into some global a that both of these are trying to figure out. It's nuanced and it's weird, and it's going to involve just one other bit of complication, and then threading that through everywhere. But that's kind of the last missing piece. But nonetheless, now I'm really done. I think I've screwed something up with the type inference there, probably, I'm guessing, in my implementation of which one? Probably apply or Lambda. One of those two cases. I got a little, I think, overeager. I think maybe this one I might be getting too many nested functions. Anywho, I'll fix that and upload it. Hopefully that was useful despite the bugs. And yeah, I'll see you next week. Thanks for hanging out. Adam should be back, and we should talk more about the Zio runtime. And maybe I'll push this up to GitHub, and if anyone wants to fix it. Okay. Bye, everybody.